So let me try guys. For the speaker, right, we will have Mr. Jagannathan. So he's the CTO and co-founder of ConnectSecure, and is a distinguished technology architect known for his USPO patents and innovation. Formerly with Siemens and Cisco, he co-developed CyberCNS for MPS at ConnectSecure, revolutionizing the NSP sector with cutting-edge optimization solution. So he's a cybersecurity, vulnerability management, and threat detection expert. So I'll now invite him to speak for us.
Thank you, Valerie. Thank you for that introduction. Good morning, everyone. So let me just quickly switch on my video. I'm just going to share my screen. So a very good morning, good afternoon to all of you, and I feel very honored to basically speak with students like you who basically are kind of the next generation of people who are going to come into this entire scenario of cybersecurity and its changing landscape. So what I will try to do today, as Valerie said, I basically am the CTO of ConnectSecure, and we basically try to solve some of the hard problems in terms of putting data together, wrangling the data, and then essentially making it something that is insightful for the MSPs. And the MSPs are a group of people who are basically IT practitioners who help the small and medium business. And when we talk about small and medium business, we're talking about up to 1,000 users. Anywhere between 50 users to 1,000 users is essentially what is the definition of small business. Medium business is up to the 1,000 to 2,500 user range. So these are the businesses that essentially fall under the ambit of this. We're not talking of very small retail businesses like single brand shops, etc., but we're talking about something which has an office. So, for example, those insights today with you folks. So, what my talk today is in cybersecurity, and what are the real world problems that we're trying to solve? Because I think talent like you is essentially is what is going to solve this problem going in the future. And I'll also talk about what are the things that we've tried, what are the different things that we put together, and what are the problems we still face, and how is this industry moving forward. So first and foremost, like if you really look at the whole AI/ML landscape, what's happening is that you will see that in cybersecurity, every vendor claims that they are using AI and ML, right? So everybody says AI based, ML based, and this is a lot of marketing hype that goes around in a lot of cases. If you really look at it, a lot of people, almost like at the marketing level, believe that if somebody has written a rule for automation, then it is essentially machine learning. The answer is no. We all know that that's not the case. machine learning is when you can essentially give a certain set of knowledge to or a model to a system, and the system can essentially generate new rules from it on its own. That's when basically we call it as machine learning or AI, and basically we make can make those distinctions. Automation is automation and cannot essentially be put into those two categories. We have a lot of the thing with cybersecurity is that it is basically filled with a lot of data. But the problem with data is basically, and which is emerging right now, is basically very long context breaks between different things. So earlier, if you look at the evolution of cybersecurity, cybersecurity is not new, right? So the attacks that exist today were some things that existed even as back in 1960s. Today, it is becoming more easier for people to access some of the tools that can be used to launch attacks, which is why you're seeing basically a lot more incidents reported. Second, there is also financial benefit in terms of attacking these systems because these have become very critical. So what has happened is that if you looked at the advent of computing, right now, if a set of services goes down, a whole bunch of people are impacted. So people are all the time on the are worried about the services going down. When services go down, reputation is spoiled. When reputation is spoiled, then it's very difficult for companies to progress further. So this is exactly the thing that is exploited by hackers so that they can get leverage, and that leverage is what they use basically in form of ransomware, or they basically send it out in form of email threats, etc. And that's how basically people fall for it, and then they basically extract data. However, as time passes by, the quantum of data that people want to extract is becoming higher because it is not just a question of uh, a simple hackers or somebody basically a script kiddie doing this. It's basically now actively being looked at by large scale governments, large scale groups, which are basically there in different regions, and they look at it as leverage. And when they look at it as leverage, what happens is that you're looking at uh, malware, which basically can be downloaded onto your system today, but does not activate for almost like 6 months or 8 months. The problem with systems like that is that there is no context, right? So all of a sudden, what would happen is that if you basically use a system which basically says, okay, so typically how do antivirus systems, how are they working? They were basically signature based. So you said, I saw the signature, and this is the executable that basically was being used. So this, if you see anything with this signature and this executable, then flag it and basically quarantine it or delete it. That's essentially how antivirus basically came into play, right? So it was signature based. The signature, then basically you have this whole concept of EDR. What does EDR do? EDR basically, if you look at most of the EDRs, they are 90% signature based. But EDRs have the ability to look at behavior. So what it says is that if itself, and it essentially makes the following changes in the registry, or it tries to make a lateral movement to another computer in the network, or it tries to basically send data to a site which is basically not something that's whitelisted, then it understands that and then it basically starts tracking it, and then it builds a signature for it, and this signature is then basically sent out to a centralized agency for terms of, is this a real threat? And once that is quantified, then all of the systems across the world basically instantly get this update saying that so take care of it. So it's doing two parts. It's basically dynamically generating a signature based on a behavior that it is seeing on a system, and then basically delivering that intelligence to somebody to basically verify, and then updating everyone else with that intelligence. So there's three aspects to it. One is to look at the behavior, second is to essentially generate that signature, and third is to distribute the signature. So those are the three concepts of what they call as an EDR. Now, the problem with EDRs today is that it's very noisy because you will get a whole bunch of false positives because For example, you basically run a Flask program and basically download it and put it on your machine. The EDR will basically say, oh, somebody is trying to basically access the system through port 8000. He's running a Flask program. We do not have um, the AI to basically look at, oh, this is a Flask program, what is it trying to do? And based on that, essentially determine whether it's a threat or not. And this is something that is still in the domain of development because it does not understand what exactly it is trying to do over there. Second, we have systems with a lot of bad input data, right? So all of you being the experts in essentially the area of AI and ML, one of the things that you know is that if you give a machine bad inputs, you will get bad outputs, right? So you can we get a lot of um, false positives that essentially plague the entire cybersecurity arena, and that is something that we constantly work on. I'll give you a very classical example. Very large vendors like some big networking vendors, etc. What you would see is that there is a format that has been defined, which is called the National Vulnerability Database. The format has been defined. It's very, very clearly defined, saying that if you report a vulnerability, you will essentially define, okay, here's a vulnerability. What is the cause of that vulnerability? What is the type of the vulnerability? And in that, there is a field which says, okay, talk about what versions of your software are impacted because of it. So you have clauses which say less than this version, greater than this version, equal to this version, and basically where is it fixed. This is essentially something that the NVD system asks you to input because uh, unless you know that, how do you create a generalized vulnerability database? Now, uh, a lot of the smaller vendors will actually put this data in. But the larger vendors, they don't put this data in. What happens is they just basically, there is a field. So for example, in the version field, if you just say star, it essentially means every version is vulnerable. Now, what happens is that a lot of these vendors basically go and put star. The moment they put that in there, anything that basically is using this for vulnerability management as vulnerable. And then what happens is customers basically come back to people and say, oh, this is a false positive. I already basically says that this particular version already patches this particular problem. Now, this is basically one of the examples of, and then the system unable, not being able to perform its task. And this is somewhere where we have started, for example, to use which models to interrogate websites and figure out as to what are the um, systems that are basically impact enrich the databases so that we can provide proper information to people on this whole thing. Main thing which I wanted to kind of security and all of the data sciences that we do, unlike with traditional systems like CRMs, etc., are very different. Cybersecurity is history is not is extremely bad for innovation here because the the way that hacker so please remember that the hackers and people who are basically attacking the network have access to the same set of tools that you have in terms of for mitigating it. So they essentially use AI to basically kind of trick the EDRs and MDRs that exist out there, and they basically also work using the same set of large language models. So the challenge is now to basically almost like as in movies, right? To catch a killer or to catch a thief, you basically need to think like a thief. And that is the exact challenge that we have, which is building AI that thinks like a person who's trying to do things and then look at what happens. And that's basically one of the reasons we essentially built something which is called an attack surface mapper. And what that does is to essentially kind of look at a company from outside and basically try to see how would an attacker attack this. Like, so we scan ports, we basically look at what ports exist, we try to get reconnaissance on what ports are open. Based on the open ports, we try to see if there's any information that comes out of those ports. Sorry.
And if any information is coming out of the ports, we essentially then take it and we basically build out the system to basically say, how can I use that vulnerability to enter the system? So that is what we do. The next thing that I just want to call about is that, as I said, everybody calls it stuff machine learning or even better artificial intelligence, but underlying most of the systems is rules and stats, and that's something that we have to steer clear of because it may be good marketing, but basically then when the systems don't upgrade themselves automatically, people feel that they're being let down. The biggest thing that you see in all of this cybersecurity is that the human aspect is still the biggest amount of work and is also the biggest risk. Why? Because when we get events and then basically these events have to be looked at by humans, and then they have to sort out what is a true event and what is a false event. If the number of events becomes very high, humans cannot handle that load. And what hackers are doing today um, is essentially overwhelming the humans who are at the SOC, because they know that it's almost like if you strongest system, if the other side basically sends 1,000 missiles, if 10 basically penetrate in, then you still have a hit ratio and you basically have caused damage. So that's essentially the problem that we are facing today with things like the SOCs, etc., where force that is required in order to keep these things at bay. And so there is an opportunity for basically a lot of machine learning to happen. But again, as I said, the whole concept is that we need to essentially bring this all together in a way that it can be used collaboratively. And when we talk about collaboratively, it is about uh, how can a machine learn just like a human? So today, humans are far better in identifying threats and basically looking at something and basically identifying that it's a threat than a machine. Now, one of the reasons that humans are better is because they collaborate, right? So they talk to multiple people, they can access multiple sources of data, and then they understand patterns. They're able to see certain patterns which they've seen in the past. So that essentially helps them to kind of create this entire system. And so what we need to look at is basically building a system which can iteratively grow, and basically which is we all almost call as an what we call as interrogative AI, which is the AI needs to start asking questions and then build its neural network and basically build its directives rather than basically going just off data. So that essentially is something that we are constantly looking at and working on. And that's basically one of the areas of cybersecurity that is out there. So if you look at it from a generalized perspective, because just to give everyone an idea of what the general industry is going towards, if you look at it, the you have supervised learning, unsupervised learning. So in supervised, you have, as I spoke about, malware classification. So you basically have but tons of samples that basically land up every day, and then you basically kind of mark false positives, and based on that, it essentially allows for things to move forward. So today, for example, if you were to release a program on the to your customers, right? You have to essentially go. A very interesting site to go to is basically a company called VirusTotal. So you will have to essentially go and put your executable onto VirusTotal if it's a Windows, or if it's a Mac or binary, the appropriate binary file, put them on VirusTotal, and then you will have to, VirusTotal will tell you whether a particular EDR or MDR will essentially flag your system as basically a threat. Now, you may be doing something very genuine, and this is something that we face day in and day out because we are a vulnerability manager, which means that we have to basically get into systems to look at if you have vulnerabilities. So we would essentially get classified as somebody who's basically a threat. And then we'll have to basically go to those systems, whitelist ourselves, and everybody's EDRs would essentially kind of send out hundreds of messages, and the system would essentially be unusable. The second area is basically spam. I'm sure that all of you encountered spam in spite of basically a lot of techniques for spam. Like even the best of providers like Google, Microsoft, they still struggle with spam because it is basically a hard problem. How do you know basically something is true or something is false? So you still have a whole bunch of items that essentially kind of become either false positives or false negatives. Third is basically there is firewalls. We all started with 100 Mbps firewalls, and today we basically are talking about 10 gig and 100 gig firewalls. And when you're talking about line rates of 100 gigs of firewall data flowing through a firewall, it is just impossible for you to basically inspect every single packet. You can put as much as of hardware that you want on it, but inspecting every single packet is not basically a viable choice. And so basically the ability to look at samples and basically flows and flow-based firewalling is something that people are basically looking at and basically getting this to scale. The areas that are there in unsupervised learning basically are DNS analytics, which talks about classifying domains and basically attaching them to uh, threat scores, and then basically seeing that. So you have things like Open DNS, which was acquired by Umbrella, and then there is something called Core DNS. All of these essentially what they do is that at the DNS level, they look at. So if you're going to resolve a particular website, right, it would essentially have intelligence that it's built through all the registries that are out there. It would essentially mark a threat level for each of them. So if something is basically marked as a threat, so if you basically type the domain name, it would essentially not give you the resolution at all. So that's how basically they try to block these kinds of things. And this is basically propagated through all the DNS servers. And so you have a secure DNS. So if it does not resolve, then you don't get an IP. And then if you don't get an IP, you can't make a connection. Now, of course, you can bypass it by basically hard coding the IP, but that's basically what the whole thing is. And then there is basically what we call as threat feeds. So you have tons of threat feeds that keep coming because some are manually curated and some are basically things which are coming from different tools. So as I said, when they look at behaviors, etc., they basically send beacons saying that these are all some of the threats that we are essentially seeing. And the ability to prioritize that and actually say that this is an actual threat versus this is not an actual threat. And something might be happening on hundreds and thousands of machines across the world, right? So when something like a bot, it's basically not one machine or two machines. It starts with a machine, but basically it becomes a botnet attack, basically goes around thousands and millions of machines, which essentially coordinate themselves into an attack. In those particular cases, deduplicating the whole thing, saying that it's not 10,000 different events, but it's a single event, and all of them are essentially part of one root on the tree, is essentially what the whole deduplication is all about. The tier one analyst actually is overworked right now because he gets all of these events and it's like looking at a needle in a haystack, right? So it's very difficult for them to find that one thing which essentially is a problem. And if they miss an event, then essentially the customers lose. So it's very easy for a customer to essentially kind of turn around and say, well, I'm paying you to do this and you've not, I still got hacked, right? And so the problem that the SOC 1 analyst faces is that just the sheer volume of data that's coming to him, even after basically putting in a lot of systems, is very high. This needs to come down by a factor of almost like 1/10 of what it is today for this to be effective. And that is an area of research that essentially everybody should be looking at. And last but not the least, it's user and entity behavior analytics. So looking at user behavior and then basically talking about how that user behavior changes things. Now, I'll give you a very classic example of what's happening in a lot of countries, right? So I don't know if you've basically seen this, like people call you saying that I'm from FedEx and the shipment that you have sent basically has illegal material. So essentially you'll have to pay. Most people basically fall fall prey to these kinds of this thing. And then there is the scam where basically somebody will does the social engineering to figure out who are your friends on LinkedIn. They will basically pose as that person on things like WhatsApp, on platforms like WhatsApp, and then ask you to buy an Apple gift card. Now, the problem is that you buy an Apple gift card, he redeems the gift card, and after that, you realize that you've been pawned. And this happens to the best of people. It's not something that's isolated to people who are not educated, but it happens to the best of people. Even highly educated people basically get into these scams. And this is something that uh, uh, should be uh, solved by the entire AI space, because what we have to do is to look at the have the ability to basically work within another Facebook chat, etc., and then identify what messages seem like and basically are fraudulent messages. That basically requires a base of understanding of how these people social engineer this whole thing and basically. So um, I basically taken a set of slides from a Black Hat conference talk. So basically, I want to give due Marty. I found no point in reproducing this over, so I'm just going to talk about this thing. So everybody thinks that AI is nothing but an algorithm. So every other day you hear a new algorithm. And I just want to point out that algorithms are nice, but if you really look at it, everything that we do in AI and ML, I would simplify it to basically say it's of these systems is essentially the concept of a map, a hash map, right? So if you really look at it, when databases started, they evolved today. Databases started with file-based databases, then they became larger, then they essentially had specific file systems, which structures they wrote to make it optimal. And then you had, when you wanted speed in retrieving data, you essentially created index. And then once you got indexes on the database, then you did fast lookups. So this is how basically databases have evolved. And you essentially language was essentially SQL. Now you can see almost a parallel equivalent of what's happening with um, the entire AI ML space, right? So we all started with uh, algorithms which essentially operated on, okay, I understood a certain set of data, I can predict certain things. We basically have more and more advanced algorithms which are using better and better forms of indexing to get to the data that we essentially need. So you're pruning trees, which means that in databases, you're doing the indexing. So as we basically keep pruning the trees and basically make, we can provide it with more context. What is different in AI from what the database evolution is database always treated all of its data as disparate pieces of data. Yeah, you had things like foreign keys, etc., but that was essentially manually defined. AI has the ability to take this to the next level in terms of being able to define new relationships and also basically learn continuously. That's essentially, so it understands what it is that you deal with AI eventually will essentially become what we call as chat GPT prompts are essentially going to be what is the equal in the databases. So what fundamentally happens with a lot of these algorithms and why, because there's a lot of assumption of clean data. That's basically the very fundamental bane to any of the AIML processes. We have seen this happening in finance. We see this happening in other fields. But in the case of security, it is basically an absolute reality that you basically cannot assume clean of unclean data. And this is because of the way that the networks are organized, the way that users basically use systems, and there are problems that exist in different systems. So let's take for an example, Windows basically went into a blue screen. Now, if you basically have to, you blue screen because of an attack which happened, then essentially when the Windows blue screen, so if you basically assume that the Windows blue screen was and the machine makes that inference, it may be true, it may not be true, and in very likely it is not true. Why? Because underlying reason for why it happened is basically a driver basically crashed. Now, why did the driver crash? Was it because of malware or was it? This is an investigation that a human can do. However, uh, a machine learning system is not equipped today to perform this because it operates purely at the data layer. It does not operate at the operation layer where it can basically kind of go out and execute a certain set of forensics and figure out like why this happened. So it is up to humans to basically make that forensics and basically give this data back. And that is essentially where the clean data will come into play. And that's where we have again and again coming to this whole concept of the way that things have to work is that it has to be interrogative AI as we move into the future. It cannot essentially be based on any past data or data that basically is not relevant in this particular case. So again, you basically, there are assumptions about types of data, this thing, and everybody basically, when we have talked about AI ML, the first thing that people talk about is all the frame TensorFlow, PyTorch, AWS, the AWS ML, and then you have basically now you have generative AI, OpenAI, all of these. Yes, great. And then you have the whole bunch of LLMs. But these are all essentially technologies underlying it. The main thing that we all have to look at is what is the problem that we need to solve and look at what is the outcome that we desire. And there are going to be cases where things like Bayesian, etc., are going to work much better than using something which is more complicated or basically more advanced just for the sake of using something which is more advanced. So I just skip over this because this is too much of information, but basically there are way different types of biases. So there is basically what we call as a sample bias. So which is basically very biased negatively or positively, and that basically causes the system to have a problem. Knowledge bias is to the system, so the system stops learning because it thinks it knows all of these parts already. And then there is what we call a history bias, which is basically I have history of how this behaved, but the future behavior might not be in this. These are basically biases that get introduced. And so again, and I'm happy that you guys are doing the Datathon because the one of the biggest challenges basically that exist have to basically get a proper data set. And a lot of times what happens is people basically develop their algorithms and everything based on data. And they basically think that if it works for one customer, it works for all the other customers. And that's exactly where things, if basically you are providing a solution for a particular customer, you can basically absolutely develop a model based on his data customer. But generalizing it, saying that that same thing which I did for that customer will work for every other customer, unless you've essentially put it out, is incorrect. And that is what that plagues a lot of the software today, because they all test it on one customer and two customers, and they declare victory in terms of, yes, it will work for everything else. And when you declare victory like that, that's when the problem occurs, because every customer's data is going to be different. And unless you have a wide cross section of data, you cannot essentially make this assumption. And we at ConnectSecure are lucky in that sense, because what we have is we have more than 2,300 to 2,400 different varied customers across geographic regions, across to kind of hone our algorithms to essentially take care of this kind of disparity. And that's essentially what we are looking at. So as we said, you could be learning from a data set that's biased or infected, and then you don't understand the being generated. And so that's essentially what we talk about. So deep learning is something, a lot of these problems. You will not succeed with deep learning if you don't have enough of labeled and quality data, right? So, and again, I said data cleanliness is extremely important. And data is very, very prone to input that is very adversarial. So it cannot basically be used to learn very easily unless you have a complete data set. And getting a complete data set, especially in cybersecurity, is very difficult. Why? Two parts. Like, do you think NSA or any of these agencies are going to release uh, data about basically any attacks that basically happen to them? The answer is no. And which are the agencies that receive the maximum number of attacks? It's basically the US agencies and US government agencies, etc. So a large part of the data in the realm of classification, the problem that occurs is it basically is something that becomes inaccessible. So what you get is signals and beacons, which are very small, which are very minute, but are blown out of proportion in terms of their severity, etc. There are far more severe attacks that essentially happen at that level. And there are large companies that essentially do this kind of research with that kind of data. However, that is not available to everyone. Second is that, like, you should basically be well trained and be an expert in this particular area. So, for example, if you're operating in security, you need to know what does an Nmap output look like? What does Nmap do? And Nmap is a tool which has been there for almost like 20 years. There's nothing which basically has come to surpass that tool in terms of reconnaissance of a network and bringing back data about open ports, etc. And then basically running some tests to figure out like what works and what does not work. So unless you become an expert and you're able to kind of give these inputs to this particular model, it is not going to be A, verifiable, B, it's not going to be something that can be interpreted and basically understood. Because the most important thing about when security events occur is that the AI must be explainable. That is, you should be able to explain the AI. And that's something that I think a lot of you will be very familiar with, which is an area that is of growth, which is called explainable AI. That is, tell me why you basically came to this conclusion. Because unless analyst can see why the AI came to that conclusion, he cannot define whether that conclusion was right or it was wrong. He cannot just work on a decision. So this is essentially kind of adversarial machine learning. So you can essentially kind of the point is that if there is enough of error in the data set, you will essentially get results which are basically highly confident. And this is something that constantly happens, especially in the cybersecurity industry. Okay. So this is the kind of data that we basically are dealing with in cybersecurity. You have network communications. You basically either pull it through NetFlow or you basically have a network tap and you will get all of these source and destination IPs. What is this thing? Usually, basically, you will not be able to see what is in the packet because it's encrypted end to end, unless you basically kind of put an ability to put an SSL proxy in between and terminate all the SSL connections and then redo the SSL connection to the endpoint. But that is essentially a little too complicated. So this is basically the kind of data that you get. Now, if you basically are able to look inside a packet, absolutely, you will essentially be able to determine what it is. But here, you have to look at the various functions of data that you have, which is what's the source, what's the destination, what's the source port, destination port, what kind of traffic is flowing. It's a TCP, UDP, ICMP. Look at the reputation of the IP address to which the traffic is flowing. What is basically, is this typical or is this atypical? And then essentially kind of come up with a model for this entire thing. And that is essentially what is the whole scope of what we do in cybersecurity. So the main thing is that most security problems, you cannot apply neural nets and basically these pieces to basically solve the problems of supervised learning, because as I've explained to you, all of the biases that exist. So unsupervised learning, yes, it basically can work, but the problem with unsupervised learning is that if your signals basically are good and they can actually cluster themselves well, then it basically, so for example, you have all of this data with terms of what source port is going to what destination port and how many bytes basically is flowing. If you basically plot it, this is how it would essentially look. Now, so basically you can compute like what is the distance between uh, like based on the source port, destination port, and the size of the traffic, you can essentially kind of put uh, create a chart like this, which essentially talks about what is the distribution of the traffic and what kind of traffic is basically flowing through. And then you can essentially use the clustering algorithms to cluster them together and then essentially identify what is anomalous traffic versus what is normal traffic. That is essentially what is basically works most of the time. And this is something that basically is a technique that we use a lot of time. And um, what is the criteria to basically choose the algorithms? It's basically what is the dimensionality of the data in terms of like here we talked about how many dimensions, the source port, destination port, source IP, destination IP, then what is the packet size, what is the type of packet. So already you're talking about 6 different dimensions. Usually the kind of dimensions that you deal with is basically anywhere between 30 and 40 dimensions because you get various enrichment data that comes in along with this. And you basically enrich it, and that's how you essentially push this data together. So the other thing is that in cybersecurity, it's like it's not a project that you run, right? So you can't just essentially say, okay, this will run, I'll get the results like 2 days later and I'm good. No, cybersecurity requires you to operate immediately. Like when there is a new kind of attack, you're supposed to basically detect and respond to it, not in 24 hours, not in 6 hours, not in 4 hours, but basically in minutes. And that is the expectation that you have when you basically deal with AI in cybersecurity. So your model should be something that essentially works at wire speed in terms of the number of packets that it's looking at, and also basically making inferences in the order of minutes, if not seconds. So that's basically the expectation. And that is why basically creating AI and ML for cybersecurity is hard, because if you look at things like financial markets and all of these, you still have time that you basically can take to basically say, I'm learning from the past. I can basically make predictions for today. I can essentially kind of give a certain guidances for today. And it's always in the guidance mode, even if you look at the algo trading, etc. And it basically executes on a plan that has been predefined for that particular day. It does not make dramatic changes unless it sees certain pieces of information that make those changes dramatically different. However, in the case of cybersecurity, every single packet has to be treated as basically new information. And basically we have to look through a complete data set to figure out like if this is something that we've seen in the past, and if it's any different from what we've seen in the past in terms of beaconing, and then basically create an operation out of it. That's basically the challenge over here. So if you don't basically understand the algorithmic parameters, what you will see is that you will essentially see uh, unclear separation. So you cannot essentially kind of understand the clustering. So if you don't get these clusters, then you can essentially not make out like whether there's a problem or there is no problem. The last one essentially shows you something which essentially cannot be clustered at all. So you essentially land up in a situation where, so if there is no clustering, you cannot make any inferences. So these are all different things that you have to take care of when basically dealing with cybersecurity. So the problem is that then what you will do is that you will basically start making decisions about anomalies like the way that they are doing over here, where you will suddenly basically take those blue dots basically along with the white dots as anomalies. And very likely that they will never be anomalies. But the problem is that there is no clear clustering that has happened in this data set. So basically you cannot essentially create an anomaly. Again, these kinds of decisions is what causes a lot of problems, which is why today it's still in cybersecurity is still in very imperfect science, because nobody can essentially tell you that I will give you a piece of software that will basically make you 100% secure. Impossible. And if any vendor claims that, that is something this thing. Can I stop most of the attacks? Most software will be able to stop most of the attacks because of the fact that if it is signature based, and that is what So what do we see today? We see that 80 to 90% of the time, these are inexperienced hackers who are basically picking up something from ChatGPT or basically some repository in the dark web and basically running a script that has been written by somebody else. So yes, so those pieces you can basically stop. What can you not stop? Very coordinated attacks by very well-researched hackers and people who essentially are people who basically come to black hat, etc. They are people who basically have experienced this. They know how to basically send the data packets, beacon it out, sleep for extended periods of time, and then basically start operating. And that is essentially what the challenge basically that is going to be there, right? So, as I said, basically doing a good clustering and being able to identify those clusters of data which are anomalous is basically the critical piece. Also identifying what are the clusters which are good so that when new data comes in, basically you're automatically going to put them into the good cluster and basically say, yeah, these data pieces are good. And then being able to isolate those particular sources which are the cause of this bad clusters is the critical piece in this whole thing. So one of the things that people are talking about for the past 5 years now, and basically is slowly taking this thing, is basically called belief networks. So creating models that represent what is the state of the world, and this is something that I basically call what I'm calling as interactive AI, where you create a graph rather than basically look at large set of tables. And this you do by interrogation, and then you use simple algorithms like Bayes' theorem to calculate what is the belief that you have in this particular thing, right? So this is what it is. So the example taken here is basically saying that I encountered basically from water falling on me. Is it coming from the sprinkler or is it raining, right? So it's basically a true or false table that basically you can create, and then you can essentially kind of uh, look at external factors, saying that is there grass around there? If the grass is around there, is there basically some sort of piping out there? Is it still basically the thing? So these are all basically methods by which you can infer and get exactly down to why something occurred. And this is exactly what we are going towards, which is basically interrogative AI and getting these questions answered by humans initially, so that this questioning sequence can essentially be understood by AI and basically taken forward going with us. So we built this graph which basically says, okay, is this port open? Is there a protocol mismatch? I have not seen this new protocol. I have not seen it for a week. It is showing up with a new operating system. Does it have any vulnerabilities that we know? Is there a mistake in the IP classification? So these are all things that essentially the system kind of is questioning and basically is interrogating and understanding. And then it basically puts the context together to make a decision. So that's essentially kind of the belief network. And then once it basically gets this state, it then can make decisions based on the belief network to essentially make an accurate representation of saying that whether a particular device is compromised or it is not compromised. And this is based on all of the information that it gets from all of these other sources, right? So again, the part is that there are pieces of expert knowledge which we are basically talking about. Then there is basically the conditional probabilities that we are putting in based on prior knowledge that we have. And then we basically have joint probabilities, which is basically more accurate. And once we put this together, then we essentially get much more accuracy. So um, belief networks or interrogative AI is something that we all should be looking at as we move forward. And then you basically get a computational goal, which basically we have. So once you basically get an inference, you continuously observe that activities on that particular host, and then you see whether that belief that you basically created is reinforced. And as you basically get more and more data points which reinforces the belief that you have, increase the weightage of what and the belief level in basically the whole thing. So you saw this, we were initially at 0.4. Once we essentially got more observation on that particular system, we essentially raised it to 0.7. What's the distinction between this and that in the earlier systems, you observed every system. You had to basically look at every system. Here, no. We only, when we basically, our belief comes to a state where we see a device is compromised, we observe it more closely, and then we learn from that particular system, and we keep increasing the belief in that particular state. And this is exactly like how I would say that investigations happen, right? So you essentially get initial piece of information. You basically kind of say, okay, this is a suspect, and then you essentially kind of drill down into the suspect pool and basically go deeper into the suspect pool, look at their history, look at where they were on a particular day and time, and then you bring all this information together to eventually kind of catch the culprit, right? So that's exactly the model that we are essentially kind of looking at with these belief networks. So as we said, we strengthen the network by using expert knowledge, and we keep asking meaningful questions. And this is what the whole belief networks is all about. So I'm just going this thing. So in summary, what we are talking about is that if you look at AI and ML in cybersecurity, um, it's a very vast field. It's basically something that requires help of all talented people like you to basically come in and basically contribute to this particular field. It is it's a lot of work in terms of understanding the dynamics of how the entire cybersecurity works, how basically exploitations occur, and as I said, you basically have to define the use cases. You have to basically combine not just one algorithm. One algorithm is never going to cut it. You're going to be using an ensemble of algorithms. You're going to be putting them together. And most important, as I've said, like we have to teach the algorithms to ask questions to experts. That is a very fundamental piece that is missing with most of the AI models that we have today. It does not ask. And OpenAI has solved this problem because OpenAI is willing to learn from you, right? So the same model has to essentially be applied back into some of these models that we have. And use whitelist and blacklist sparingly, because there are a whole bunch of problems with whitelist and blacklist that are out there. And then basically sharing models between multiple people will basically get you to solve the issue of that you have a bias with a single customer, and this will essentially be what it is. And of course, the whole point is that while you have all these models, that you basically kind of follow the GDPR and basically personal information hiding, because you don't want to get into problems. So these are some sound bites which basically came from the Black Hat last year, which is algorithms are smarter, but basically use the expert. And that's where we said the algorithms have to basically be able to query the expert, understand your data, the algorithms, and the data science process. Last but not the least, basically, it's not all about history. It's not a predictor. Knowledge is a predictor. History is not a predictor of what's going to happen in the future. So if we basically were to determine the future based on all the past wars that occurred, then we should be having many more wars than what we're having today. So context of what the current date and what is relevant at the current date and time is basically very important in terms of what we do. So this is basically what I wanted to kind of talk about today. I'm happy to take any questions or any queries that anybody may have.
Are there any questions from the audience? If not, right? I'd basically like to take this opportunity to thank Mr. Jagannathan for sharing his expertise on the applications of AI and ML in a very, very interesting and upcoming field. So thank you all for coming, and especially thank you to Mr. Jagannathan for his time. All right.
Thank you very much. Have a great day, guys.
If there's anything else any questions and so on, we'll just be in the call for another few minutes. Else, thank you so much and have a good Datathon, guys.